Hello my dear friends. In my last video, we have revised some of the concepts of thermodynamics and mechanics of fluids required for this subject. I have also introduced the three approaches in thermodynamics: the continuum approach, the systems approach and the control volume approach. In continuum approach, similar to the macroscopic approach, we are not at all concerned with the molecular level activities of the fluid. We consider the fluid as a whole. Now coming to the systems approach, here the space for study is separated from the outside world. We call that space by the term system, and everything outside that space is called surroundings. Which separates the systems from surrounding is known as the boundary. There are three types of systems: the open system, closed system and isolated system. And the last approach is the control volume approach, which is the most important approach as far as this subject is concerned. In control volume approach, there is the exchange of matter and energy through the control surface. It is similar to the open system. Now, there are four different types of control surfaces. The control surfaces may be real or imaginary, or fixed or moving. And now, today in this video, we are going to discuss some of the fundamental terms and equations in this subject. Let us start with the term Mach number. Almost all of you have heard this term Mach number. This term was named after the Austrian scientist Ernst Mach. He defined Mach number as a dimensionless number whose value is the square root of ratio between inertia force due to the flow and the elastic force of the fluid. So the expression for Mach number m is equal to square root of inertia force by elastic force. The expression for inertia force is equal to rho a c square, where rho is the density, a is the area of cross section and c is the velocity of the object. So here we have to note that it is not v but c the velocity. In this subject, the velocity will be notated by c throughout. And the elastic force is equal to k into a, where k is the bulk modulus, whose value is equal to rho a square, where rho again is the density and a, small letter a, is the velocity of sound in the medium taken. And so the expression for Mach number will be equal to square root of rho ac square divided by rho a square. So cancelling the common terms, we will be obtaining Mach number m is equal to c by a. We can define Mach number at a point in the flow field as the ratio of local velocity, which is notated by c, at a location under consideration to the velocity of sound notated by a in the medium at the same location. So that is the expression for Mach number, and this is the most important expression in this subject. M is equal to c by a, where c is the velocity of the object or fluid under consideration divided by a, where a is the velocity of the sound in that medium. Now in a later video, I will be showing that the velocity of sound is equal to root of gamma r t, where gamma is the ratio of specific heats, r is the characteristic gas constant and t is the temperature. So finally, the most important expression for this subject, Mach number m is equal to c divided by root of gamma r t. Now let us discuss about the energy equation. Consider a control volume as shown here. Now the fluid enters the control volume with a velocity c1. The other properties at the inlet are h1 and ρ1, where h1 is the enthalpy and ρ1 is the density. Fluid exits the nozzle at velocity c2 and the corresponding properties are h2 and ρ2. So here you can see a datum. Now it is used to represent the height or the elevation of the object. So the elevation at the inlet is equal to z1 and that at the exit is equal to z2. The shaft work is equal to Ws. We know the total energy in a system is the sum of internal energy, potential energy and kinetic energy. That is, E is equal to U, that is the internal energy, plus mgz, that is the potential energy, plus half mc square, that is the kinetic energy. So that is the expression for total energy of the system. Now let us differentiate this expression. So we will be obtaining dE is equal to du plus mg dz plus half m dc square. Now let us try to integrate the above expression with respect to the limits 1 and 2. 1 represents the condition of the control volume at the inlet and 2 represents the condition of the control volume at the exit. So while integrating, we will be obtaining integral dE is equal to integral du plus mg integral dz plus half m integral dc square. Now let's apply the limits. E2 minus E1 is equal to U2 minus U1 plus mg into Z2 minus Z1 plus half m C2 square minus C1 square. Now, according to the first law of thermodynamics, we know the heat transferred is equal to the work done plus change in energy. That is, heat transferred Q is equal to work done W plus change in energy E2 minus E1. So here in this expression for first law of thermodynamics, we have a term E2 minus E1. But we have already derived the expression for E2 minus E1. Now let us substitute the expression for E2 minus E1 from the expression 4 to the fifth expression. We will be obtaining Q is equal to W plus U2 minus U1 plus mg Z2 minus Z1 plus half m C2 square minus C1 square. And this expression is known as the energy equation. Now let us try to rewrite this expression in specific terms. So what do you mean by specific terms? That means the terms corresponding to mass equal to 1 kilogram or mass of unity. So one thing you have to note while rewriting an expression in terms of specific values is that all the capital letters will be replaced with the small letters. Because the heat transferred Q, that capital letter Q indicates the total heat transferred, whereas small letter q indicates the heat transfer per kilogram. So the final expression is Q is equal to W plus U2 minus U1 plus, there is no M because M is 1. We are speaking about specific terms where the mass is unity. G into Z2 minus Z1 plus, again there is no M, half C2 square minus C1. So this is the energy equation in specific terms. And you have to remember the sixth expression, that is the energy equation. Now let us write the energy equation in terms of a non-flow process and a flow process. First, about the non-flow process. You know, a non-flow process is the process happening inside a closed system. So in such systems, we can neglect the values of kinetic energy and potential energy. The work done is only the shaft work, which is indicated by Ws. So neglecting the terms of potential energy and kinetic energy, that is the third and fourth terms, we will be obtaining Q is equal to Ws, because for a non-flow process, work done is only the shaft work indicated by Ws. So Q is equal to Ws plus U2 minus U1. You can neglect the terms of kinetic and potential energies. Now let us discuss the energy expression for a flow process. You know that the flow process is the process taking place inside an open system. So in an open system, the total work done includes two things, that is the shaft work as well as the flow work. So W is equal to Ws, that is the shaft work, plus P2V2 minus P1V1, that is known as the flow work. So the work term includes these two terms, that is the shaft work and flow work. Now let us substitute this expression for W in our sixth equation. So we will be obtaining the expression for heat transferred Q as Q is equal to Ws plus P2V2 minus P1V1. That is the term indicating the work, the total work, plus the remaining all terms, that is U2 minus U1 internal energy, mg Z2 minus Z1 potential energy, plus half mc2 square minus C1, that is nothing but the kinetic energy. Now you can rewrite this expression. I am clubbing the two terms P2V2 along with U2 and P1V1 along with U1. So why should I be doing that? You know the expression for enthalpy H is equal to U plus PV. So we can substitute the expressions for U2 plus P2V2 by H2, and you can substitute U1 plus P1V1 by H1. So the final expression will be Q is equal to Ws plus H2 minus H1. We have substituted the terms U2 plus P2 V2 minus U1 plus P1 V1 with H2 minus H1 plus the remaining terms, which are the potential energy term and the kinetic energy term. Next, I am going to rearrange this expression such that all the ones come at one side of the expression and all the twos comes to the next side of the expression. So, while rewriting, there are few terms which have no 1 or 2, that is Q and Ws. So, the equation rewritten will be like this: H1 plus mgz1 plus half mc1 square plus Q is equal to, so I have put all the 1 terms to one side of expression along with the heat transfer, is equal to the other side H2 plus mgz2 plus half mc2 square plus Ws. So, I have put the shaft work term Ws along with the terms having suffix 2. Now, this is the expression for flow process, energy equation for flow process. You can again rewrite this expression in terms of the specific values. That means you can rewrite this expression where m is equal to unity, mass is equal to 1. So, the expression will be in like this: H1 gz1 plus half c1 square plus q is equal to H2 plus gz2 plus half c2 square plus Ws. All the terms will be in small letters because we are writing in specific values. Now, let us rewrite this expression for an adiabatic process involving only energy transformation. So, from the above expression, you can cancel all the terms including potential energy and work transfer, which means the terms including Gz1 and Gz2 can be neglected. Ws can be neglected because there is only energy transfer, no work transfer, and the term Q can be neglected because in an adiabatic process there is no heat transfer. So, the expression for an adiabatic process will be H1 plus half C1 square is equal to H2 plus half C2 square. And this expression is known as steady flow energy equation or SFEE. And this is a very important expression as far as this subject is concerned. Next, let us discuss about the stagnation conditions. Stagnation conditions is as important as Mach number for this subject. Stagnation condition can be defined as the state attained by isentropically decelerating a fluid to zero velocity at zero elevation. So, this expression or this definition is extremely important. I have pinpointed 4 points in that definition. So, we are decelerating, the first term, decelerating a moving fluid to zero velocity at zero elevation, and the process is done isentropically. So, these are the 4 important terms for the definition of a stagnation condition. Now, the concept of stagnation condition defines a convenient reference state for the flowing fluid. We have to define all these types of stagnation condition, starting with stagnation enthalpy, temperature, pressure, density and velocity of the sound. All these are having some minor derivations which can be ended up with 3 or 4 steps. So, let us start with stagnation enthalpy. It is the enthalpy of a gas when it is isentropically decelerated to zero velocity at zero elevation. So, there is absolutely no change in the definition. Now, let us try to derive an expression for the same. This is the expression from steady flow energy equation. H1 plus half C1 square is equal to H2 plus half C2 square. H1 in the above expression with H and C1 with C, that is for the initial states, and coming to the final states, you are decelerating the fluid to zero velocity. So, the velocity C will be equal to 0 and the corresponding enthalpy H is known as stagnation enthalpy, which is indicated by H0. So, all the stagnation properties are represented by suffix 0. So, the steady flow energy equation after making these changes will be like this: H plus half C square is equal to H0. That is nothing but the stagnation enthalpy. So, this expression is very important. Now, let us move to the next expression, stagnation temperature. Definition the same. The temperature of a gas when it is isentropically decelerated to zero velocity at zero elevation. Now for derivation, we are starting with the expression for stagnation enthalpy. H0 is equal to H plus half C square. But we know the expression for enthalpy, capital H is equal to mCp dt. In terms of specific values, enthalpy small letter h is equal to Cp into dt. So from that expression, you can write the stagnation enthalpy H0 is equal to Cp into T0. Therefore, the expression for stagnation enthalpy can be rewritten as Cp T0 is equal to Cp T plus half C square. So we have rewritten the expression for stagnation enthalpy along with the terms of Cp. Now we are dividing the entire expression with the specific heated constant pressure Cp. So this is the expression T0 is equal to T plus C square divided by 2 Cp. The next step, we are dividing throughout with T, the temperature. So we will be obtaining T0 by T is equal to 1 plus C square by 2 Cp T. Now you know the specific heated constant pressure Cp is equal to gamma R by gamma minus 1. So you can substitute the value of Cp in the above expression. So the expression for T0 by T can be written as 1 plus gamma minus 1 into C square by 2 gamma RT. But we know the velocity of sound A is equal to root of gamma RT. So the term in the denominator can be changed. So the final expression for T0 by T is equal to 1 plus gamma minus 1 by C square divided by 2A square. But C square by A square, you know C by A is equal to the Mach number m. So C square by A square is equal to m square. And the expression for stagnation temperature T0 is equal to T into 1 plus gamma minus 1 by 2 into m square. So that's about the stagnation temperature. Now let me explain stagnation pressure. Stagnation pressure is defined as the pressure of a gas when it is isentropically decelerated to zero velocity at zero elevation. For obtaining the expression, you can take the expression for an isentropic flow connecting pressure and temperature. P2 by P1 is equal to T2 by T1 all raised to gamma by gamma minus 1. Again, the substitutions to be made. For the initial state, you can substitute P1 is equal to P and T1 is equal to T. And for the final state, as I told, we are decelerating to zero velocity. So the conditions obtained will be corresponding to the stagnation conditions. So P2, the stagnation conditions will be equal to P2 is equal to P0 and T2 equal to T0. So that is the change to be made in the final stage. So the expression can be rewritten as P0 by P is equal to T0 by T all raised to gamma by gamma minus 1. But just before, we have seen an expression for T0 by T and we are substituting that expression in the above equation. So P0 by P will be equal to 1 plus gamma minus 1 by 2 into m square all raised to gamma by gamma minus 1. So making sufficient changes, you can obtain the expression for stagnation pressure P0. Next is the stagnation density. Definition: stagnation density is the density of a gas when it is isentropically decelerated to zero velocity at zero elevation. Again, for derivation part, we are taking the expression from isentropic flow connecting density and temperature. Rho2 by Rho1 is equal to T2 by T1 all raised to 1 by gamma minus 1, expression from isentropic flow. Now we are making the changes as told before, substituting Rho1 with Rho and T1 with T for the initial states, and for the final states, as we are decelerating to zero velocity, the final state will be corresponding to stagnation conditions. So the density Rho2 has to be changed to Rho0 and temperature T2 has to be changed to T0, the stagnation properties. Now this is the modified expression. Rho0 by Rho is equal to T0 by T all raised to 1 by gamma minus 1. And the expression for T0 by T we have already seen while defining stagnation temperature. We are making substitution in the above expression. So this is the expression for Rho0 by Rho. So the stagnation density Rho0 is equal to Rho into 1 plus gamma minus 1 by 2 into m square all raised to 1 by gamma minus 1. That's about stagnation density. And the last stagnation property is stagnation velocity of sound. So here the definition is a little bit different. It is the velocity of the sound corresponding to the stagnation condition of the section. Okay, now let us try to derive an expression for the same. Velocity of the sound A is equal to, that is equal to root of gamma r t. Now, to correspond to the stagnation conditions, you have to make some substitutions. A has to be substituted. The velocity of sound A has to be substituted with A0 and the temperature T has to be substituted with T0. Therefore, the modified expression will be equal to A0 is equal to root of gamma r T0. But the expression for Cp, the specific heated constant pressure, is equal to gamma r by gamma minus 1. Therefore, r is equal to gamma minus 1 by gamma into Cp. So, we are making modification in the previous expression for A0. A0 is equal to root of gamma into gamma minus 1 by gamma into Cp T0. Cancelling the terms, and we know the stagnation enthalpy H0 is equal to Cp into T0. So, making such modifications, we can get the expression for stagnation velocity of sound A0 is equal to root of gamma minus 1 into H0. And you don't have to by heart all the final expressions corresponding to the stagnation conditions, because all these formulas are available in your data book. But you need to know about the derivation, how you derived at the final formula. We are ending today's session with one more small and yet very important derivation, the kinetic form of steady flow energy equation. The expression for specific enthalpy H is equal to Cp into T. That can be rewritten as gamma r by gamma minus 1 into T, because Cp is equal to gamma r by gamma minus 1. And in the numerator you can see gamma RT, which is equal to A square, the square of velocity of sound. So, the expression can be written as H is equal to A square by gamma minus 1. So, now you have got two expressions for H. One is Cpt and the other one is A square by gamma minus 1. Now, coming to specific enthalpy, which is equal to H0 is equal to H plus half C square. So, the H in this expression can be rewritten in the above two forms. The first one is H0 is equal to Cpt plus half C square, and the other one is H0 is equal to A square by gamma minus 1 plus half C square. I have indicated one expression in the red color and the other expression in violet color. And now I am going to divide this expression into two parts. In the first part, we are taking the temperature T is equal to 0. If temperature T is equal to 0, H, the enthalpy is also equal to 0, because H is equal to Cpt. And then if the temperature is equal to 0, the velocity will be corresponding to the maximum velocity Cmax. Why? You can see the expression for enthalpy H is equal to Cpt plus half C square. If the term T is getting cancelled, the first term Cpt will be removed from the expression. So, what remains is equal to is H0 is equal to half C square. So, that velocity corresponds to the maximum velocity. So, H0 is equal to half C max square, or in other words, C max is equal to root of 2H0. Now, coming to the second expression indicated in the violet color, when C is equal to 0, the other side, when C is equal to 0, all the properties will be corresponding to the stagnation property, because when velocity is 0, the condition is equal to the stagnation condition. So, if C is equal to 0, the velocity of sound A will be equal to A0, the stagnation velocity of sound. So, the expression for H0 can be rewritten as A0 square by gamma minus 1, as indicated in the second expression, the violet color expression. So, finally, you can club all these expressions for H0. H0 is equal to A square by gamma minus 1 plus half C square, that we have already seen, and that is equal to half C max square, the one indicated with the red color, and the last one, that is equal to A0 square by gamma minus 1, the one indicated by the violet color. So, these are the three different expressions for H0, the stagnation enthalpy, and this expression is known as the kinetic form of steady flow energy expression. And with this, we have come to the end of today's classes. So today we have discussed few things which form the basis of the subject, starting with Mach number m, then the energy equation. From that we have derived the steady flow energy equation SFEE and also the kinetic form. And also we have discussed some of the stagnation conditions. So all these things are really important and will be highly useful in the upcoming videos. So I hope you have enjoyed this video and have a nice day. Thank you.